Good morning, everyone. My name is Carlos Hoppen. Before I start, I would like to thank the organizers of ICALP 2020 for their effort in bringing this conference online. And so I hope everybody who is watching is safe and their friends and family are safe as well. So today I'm going to talk about efficient diagonalization of symmetric matrices associated with graphs of small treewidth. This is joint work with Martin Fürer, whose photograph is on the bottom left, and Vilmar Trevisan, whose photograph is on the bottom right. So my talk will be divided into three parts. So I'll start talking about some motivation of spectral graph theory and eigenvalue location. I'll mention graph decompositions, and then I'll present the algorithm, which is the subject of this paper. So when we talk about spectral graph theory, it's important to mention that graph eigenvalues and eigenvectors have a large number of applications, both within graph theory and in other areas. It's really a large number. I just mentioned a few here. So graph isomorphism was one of the reasons why people started considering graph spectra. Eigenvalues are useful bounds on NP-hard parameters like coloring, domination, independence. For data mining and image segmentation, one can use eigenvectors to get good partitions. Data classification is also a source of application, so PageRank and other algorithms, molecular descriptors in chemistry, expander graphs, and so on. And of course, in any such application, computing eigenvalues and eigenvectors or finding good estimates are important, right? So that's what we're going to talk about today. To get started, I have two basic definitions. One is of similar matrices. So two matrices A and B are said to be similar if there is an invertible matrix M such that A is the product M times B times the inverse of M. And two matrices are said to be congruent if there is also an invertible matrix N such that A is equal to N times B times N transpose. So we have N transpose instead of the inverse. And a very well-known theorem, and very basic in linear algebra, is that if A and B are similar matrices, then they have the same eigenvalues. If they're congruent, it's not true that they have the same eigenvalues, but a node result of Sylvester, so from 1852, tells us that at least the number of positive eigenvalues, of negative eigenvalues, and of eigenvalues equal to 0 is the same. And more generally, we can use that for a given symmetric matrix A and the real number C to determine the number of eigenvalues of A greater than C, less than C, and equal to C by computing a diagonal matrix that is congruent to A minus C times the identity. And we can run this procedure twice for two values of C, to being the endpoints of an interval. And this procedure allows one to find for any real interval I, the number of eigenvalues that lie in I. And this is called eigenvalue location. So eigenvalue location has been investigated in the spectral graph theory community, and especially there are algorithms that work on graph classes. I would like to mention a result in the direction of ours, and that's by the three authors here and Jacobs, and it used the click width of a graph. So I'm mentioning more about that later. Okay, so what's the problem? The problem is to find a linear time algorithm to compute a diagonal matrix D that is congruent to a symmetric matrix M of order N associated with a graph with a convenient decomposition. So linear time related with convenient decomposition. And when we say matrix associated with a graph, what we mean is we have a matrix, in our case will be symmetric, they're like on the left. We have the non-zero positions marked, and we create a graph where the vertices are indexed by the rows and columns, and each vertex A is incident with adjacent to vertex B, if the entry AB and of course BA in the matrix is non-zero. We ignore the diagonal, so there are no loops. Okay, so one other problem that is quite related with what we're going to talk about today is Gaussian elimination. So everybody knows that from basic linear algebra. And the idea is to start with a matrix, and we want to find a row reduced matrix in row echelon form. And to do that, we use diagonal elements to cancel out the other elements in its column, doing elementary row operations. So in this case, for instance, if A11 is non-zero, we can use the first row to eliminate all the other rows. And if we do that, the number of operations will be of cubic order if we have an n by n matrix. And here in this slide, I'm assuming that all pivots are non-zero, and you see why. And a question is, if I knew something more about the matrix, for instance, if it's sparser and there are many zeros there, can I use the graph to get a better algorithm? So that has been investigated a lot, and I'm going to talk about that a little bit. So the graph decomposition I'm going to use is the tree decomposition. And a tree decomposition of a graph G is a tree T with nodes 1 to m. And each node is associated with a bag. So we have bags B1 to Bm with the following properties. So each vertex of the graph is in some bag. So the union of the bags is the entire vertex set. Every time I have an edge in the graph, the pair of vertices must be in some bag. And given a vertex in the graph, if I look at the subgraph of T induced by the nodes whose bags contain X, it must be connected. And the width of a tree decomposition is the maximum size of a bag in the decomposition minus 1. And the complexity of the graph, or the parameter that measures it, the treewidth, is defined as the width of a decomposition that has minimum width. So that's the best decomposition. So here we have an example. So the same graph that we had before on the left, and that we have a tree decomposition on the right. So I wanted just to call your attention for the fact that B is green. And if we look at the nodes that contain B in the tree, we see that that's a connected graph. And also that we have the edge EG, and we can see that the vertices E and G lie in two bags on the decomposition, and that's true for every edge and every node in G. So that's a tree decomposition, and the width is 2 because the largest bag has size 3. And unfortunately, finding a tree decomposition of a graph with close to the tree width is a hard problem. So we have a reference for NP hardness, and a large number of approximation results are in the literature. So what's the relation between Gaussian elimination and tree width? So we have the matrix that we had before, the associated graph, and the tree decomposition of the graph. And let's look at the positions AA, DD, and so on, the diagonal positions on those rows. And let's look at their elements in the tree decomposition. So we can see that A is in a single bag. And if we look at A and we use that diagonal element to eliminate the elements in rows B and C, what's going to happen is that it will affect other positions in rows B and C, but the only positions that can be affected are the ones in B and C, like here. And those are precisely the nodes that lie in this bag. And the same would happen for D, right? If we use D and we try to eliminate those two elements, then we are going to change only these positions over here. So the positions change are only in the bag. And so we can use those elements to annihilate other elements in their rows. Of course, we are always assuming that those elements are non-zero, and that's why they can be used to annihilate the elements of the other rows. Okay, so I just changed the order here of the matrix. I rearranged so that we can see what we have done so far. And now, if I label my tree here bottom up, so I start from the leaves and I'm going up to the root, then the next vertex would be 5, and G is the element that disappears. And so that would be the time where I try to use this element to eliminate these other elements that are in its own row. I don't need to eliminate those because they're already in row echelon form here. I already have the pivots. So I eliminate those, and those are precisely the elements that are in the bag. So if we continue like this, it's not hard to get convinced that if every time I try to eliminate, I had a non-zero element here, the only operations I have to do are in this submatrix induced by those elements. So it would be something of order k squared, and I have an element, so that would be the number of the complexity of putting the row in the matrix in row echelon form if all the elements were non-zero. And that's a big if, so we don't have an algorithm like this. So the problem is find an algorithm of complexity order k squared n to perform Gaussian elimination in a matrix of order n associated with a graph with treewidth k. And as I mentioned, there is so far no solution for that, but there is a recent result by Fomin, Lokshtanov, Philip Suk, Saurab, and Fruchna, and they give an order k cubed n algorithm. I should mention that their algorithm is for Gaussian elimination in general matrices, so they don't need to be square and they don't need to be symmetric. And their graph is a little bit different because using non-symmetric matrices creates not the need, but it's natural to consider a bipartite graph where the bipartition are given by columns and rows. Anyway, so I should also mention that the tree decomposition is always part of the input. As I mentioned before, it's hard to compute in general. And this fits into FPT within P, which investigates fundamental problems that are solvable in polynomial times, but for which a lower exponent may be achieved using an FPT algorithm that is also polynomial in terms of the parameter k. So there has been quite a bit of interest in this. Let's come back to our objective. So here, we'll find an algorithm with complexity order k squared n to compute a diagonal matrix that is congruent to a symmetric matrix M of order n associated with a graph with treewidth at most k. So it will be similar to the algorithm I described for Gaussian elimination, but we'll have to operate on rows and columns to keep congruent, and we'll be able to deal with the zero elements in the diagonal. So let M be a matrix with underlying graph G. So the algorithm computes a diagonal matrix D congruent to M. It does this through elementary row operations, followed by the exact same elementary column operations. The algorithm uses a tree decomposition T, a special one, it's called edge explicit, of the underlying graph with width K and works bottom up in T. At each node, the algorithm initializes a matrix or produces a new matrix based on the matrices transmitted by its children. Okay, so let's see an example. So here I have a matrix. I have the graph associated with that matrix. And I also have tree decomposition that is a nice tree decomposition in the sense of clocks. Our is a little bit different. I'm not going to show exactly the difference, but I'll mention it later. So in a nice tree decomposition, we have 4 kinds of nodes. So the leaf nodes, forget nodes, introduce nodes, and join nodes. And leaf nodes are the ones where you get started. So you start with some bag. When you have a forget node, it means that you have a child and you forget one of the vertices that are in the bag. So in this case, 2 is not anymore, so 2 has been forgotten. Introduce means introduce a new vertex, and in this case, it's 5 that has been introduced. And join means that we have two bags that are the same, and then we join them into another node that has the same bag. And that's a nice tree decomposition. And it's a fact that given a decomposition with m nodes and with k of an n-vertex graph, one may find such a decomposition with at most 5n nodes in this number of operations. And 5n also counts these edge nodes that we have in an edge explicit decomposition, and which I'm going to talk about a little bit later. Good. So let's understand what's the structure computed at each node. So at node T with bag BT, the algorithm produces a matrix NT. And the matrix is as follows. I have two square matrices, N0 and N2. N0 is a matrix of order K prime. And those vertices will be called type 1, and it's all zeros. So that's a matrix all of zeros. This is also a symmetric matrix, and this can have other entries. But what's important is that the rows and columns of N2, they are labeled by the vertices in the bag. So the vertices in the bag correspond to this. And N1 is going to be a matrix in row echelon form. For you to understand, those are the ones in the bag that we are considering right now. And those are the ones that we didn't get a chance to diagonalize because we had 0 in the diagonal. So they're waiting here until they can be diagonalized. And an important feature is that the number of rows and columns here is always smaller, less or equal than those, and that's why we are keeping row echelon form here. And therefore, this matrix has size bounded by 2 times k plus 1, where k is the treewidth. So nodes of type leaf and introduce vertex simply include new rows and columns into the matrix corresponding to the vertices added to the bag, and they are all type 2. And nodes of type introduce edge change the entries between two type 2 vertices. And that happens when the algorithm realizes that they are adjacent. And the algorithm needs to realize that quite late. And that's why we have the introduce edge to mark the time when the algorithm realized that they are adjacent. And nodes of type forget try turn the forgotten vertex into a pivot. If the diagonal entry is non-zero, the algorithm succeeds. If the diagonal entry is 0, the vertex turns to type 1, and we have to do other things. And while processing nodes of type forget and join, one or more vertices of type 1 may be diagonalized as the algorithm keeps N1 in row echelon form. Okay, so let's look a little bit more at forget. That's an important operation. So let's suppose my node forgets V. And so that's the time I want to diagonalize the row and column related with V. So when the matrix came from the child, that was a type 2 node, and it was in the bag, and now I have to remove it from type 2. And I'm going to try to diagonalize it. If it's non-zero, I had mentioned, oh, I can use it to eliminate those elements here. A problem would happen, at least in the structure of my algorithm. It would happen if we had to remove elements here, because perhaps those elements here could mess up with these elements over there. So we have to take care of the fact of xv being 0 or not. So if we only have zeros here, then we have no problem. And if dv is non-zero, we can diagonalize. If we have 0 here, but we also have zeros here, what we do is v becomes type 1, and we need to insert them in a way, so we will have zeros here to keep row echelon form. If this is not 0, and here it could be 0 or not, and I wrote 0, but it could be non-zero, but if it's not 0 here, what I'm going to do is to take the last element that is non-zero from left to right, And I can use it to eliminate these other elements. And here I would eliminate those two. And I can do it in a way that I don't mess up with the structure. And so that's important. And then what I do is as follows. If it's non-zero here, I can just diagonalize. But if I have 0 here, and then now I will only have a single non-zero position here, single non-zero position here, but it will be 0 here. So I have a submatrix like this. What I can do is use a trick where we use 2 row and 2 column operations to get from a submatrix like this to a submatrix like this without changing the structure. And now we have non-zero elements in the diagonal, and we can use them to diagonalize. And the fact that this works for symmetric matrices and it works for congruence is because we need this trick to get this matrix into this matrix here. So operation join only means that we have 2 type 1 parts. Both are in row echelon form, and we have to merge them. They are disjoint, so that's part of the tree decomposition. And because of that, we only need to merge those 2 things. And here we'll possibly create rows and columns full of zeros. So to finish, I wanted to mention that we devised an order k²n algorithm that finds a diagonal matrix D that is congruent to a symmetric matrix M of order n, associated with a graph with treewidth at most k. And the natural question is to find a similar algorithm for Gaussian elimination in general matrices. And it would be nice to consider other decompositions or graph classes. As I mentioned, there is a result using clickwidth, but it's much less general than this, the type of matrix that we can consider. There are many applications to spectral graph theory, so these kind of things have been used for bounds on the indices, energies, multiplicities, so those algorithms can be useful in that direction. And the trend of studying problems FPT within P is an important one, and one can find natural and sometimes beautiful algorithms in this direction. So thank you very much for your attention. It was a pleasure.